Okay. Good morning, everybody. It is 11:10 on Monday morning. I can see the sun shining out there in Toronto, but it was very cold and there was a lot of ice on the ground. So it's been said, I used to live in Edmonton, and in Edmonton, the saying is that there is no such thing as cold weather. There is only inappropriate clothing. So I have my mitts, my scarf, I had my ski helmet. I actually have a downhill skiing helmet, which I got used, which is good for this time of year, and a nice coat. And I just went really slowly. Normally my bike ride takes about 20 minutes. Now it takes about 35 minutes because I just go really slow through the ice because I don't want to wipe out. I'm gonna turn off the chat, but I can still see the chat from my end. I do appreciate what people are going through. I don't know what the Apple stuff is all about. Okay. Yeah, I want to talk a little bit about midterm 4 today, which will be after the reading week. Let's do a poll question just to kind of get us a little woken up here. So, a firecracker explodes in midair and suddenly breaks up into many fragments. Which of the following statements are true regarding the conditions immediately before and after the explosion? Is it 1, the total momentum of the fragments is equal to the original momentum of the firecracker? 2, the total kinetic energy of the fragments is equal to the original kinetic energy of the firecracker? Or is it, I guess, A is neither statement is true, and D is that they're both true? Okay, let's see what you guys say. Give another 10 seconds to click in, please. What you thinking about this? So you got about 400 people on the call, so good morning. And about 83% of you have voted in this poll about the firecracker. Is it momentum or kinetic energy or what is conserved? And polling. Share results. So the most popular answer is B, and that is absolutely correct. If the 45% of the 152 of you voted for B, I like it. So the reason here is, okay, that basically during a collision or explosion, okay, the external impulse is usually pretty small. And I'll just say can be neglected. So this is a little bit due to this idea of immediately before and immediately after. Now, it is true that gravity might be pulling, accelerating the firecracker. But if the duration of the actual explosion, which goes pow like that, is very, very small, then the delta T of that gravity force will be very, very small. So the impulse would be very small. So in collisions and in explosions, we normally neglect the outside impulse and we say that the total momentum is conserved. But what definitely is not conserved here is kinetic energy. There's a lot more kinetic energy, and what happens is that chemical energy, internal energy, is converted to kinetic energy. Is converted to kinetic. So the kinetic energy of all the fragments is often much, much greater than the kinetic energy of the original firecracker. Okay, good. The other thing I wanted to do is finish off this demonstration. Remember, I had the basketball and the tennis ball together. I dropped them, and the tennis ball ended up going up with a much higher velocity than the basketball. And that was due to these equations. So you have a 0.5 kilogram basketball which is moving upwards. I'm going to say that ball 1 is the basketball and strikes a 0.5 kilogram tennis ball initially moving downwards at 4 meters per second. They have an elastic collision. What is the speed of the tennis ball immediately after the collision? So I'm going to call 2 the tennis ball. And what I'm going to do, I'll sketch the initial and the final situations. Initial and final. So initially what's happening as described is you've got 2 and 1. 2 is going down, 1 is going up. V2 initial, that's the tennis ball, is -4 meters per second. I'm going to define plus y to be up. And then V1 initial is equal to, so the second one's an I there, is equal to +4 meters per second. And then finally, we've got 2 is going up. That's the tennis ball. That's what we actually want to find is V2 final equals question mark. And then 1 will be doing something. I think the basketball is also going up at the end of it, but V1 final, we don't care about. We weren't asked about it. For some reason, after this collision happens, no one cares what happens to the basketball, but the tennis ball is doing something interesting. So what we do here is that we're going to use these equations, but they only work if ball 2 is initially at rest. So let's switch to a reference frame where ball 2 is at rest. Initially. To do this, all you have to do is initially ball 2 was going down with -4 meters per second, -4. So if you +4 to that, you'll get to 0. To do this, just +4 meters per second to all y velocities. So that's easy. And then what you have to do here is remember to -4 meters per second at the end to get back to the lab frame So this is a little physics tricks to get back to the lab frame. So the physics trick is we first add the +4 meters per second to switch into that tennis ball frame just before the collision. Then we use these nice equations, which give us final velocity. But then don't forget to -4 meters per second to go back into the lab frame so you know what really happened to the tennis ball. It's just looking at it from a different perspective. So in the ball 2 initial rest frame, what it looks like is I'm going to call it primes. V2 initial prime is equal to 0. And V1 initial prime is equal to 4 + 4 is actually +8 meters per second. So relative to the tennis ball, even though the basketball in the lab frame is moving up with 4, relative to the tennis ball frame, it's moving up with +8. So that's interesting. Then we just use this equation right here. And we see that V2 final prime, the prime reminds you that you're in this weird reference frame, is 2m1 divided by m1 plus m2 times v initial prime. So that's equal to 2 times 0.5 divided by 0.5 plus 0.05 times 8. So I plugged all that into my calculator and I got V2 final prime is equal to plus 14.5 meters per second. So convert back to the lab frame by just minusing. V2 final is equal to 14.5 minus 4 meters per second, and I got plus 10.5. So it's still pretty fast. So that's why the tennis ball flies up really fast with 10.5 meters per second. Okay. Jerry, how's it going?
Good morning, sir. Ask about like how do you arrive at those two initial equations, like those two?
That's a good question. So that we did last time. What those equations come from is conservation of momentum. So the total momentum of both balls is equal before and after the collision, and conservation of kinetic energy, which looks kind of the same, except you've got, instead of m1v1 plus m2v2, you've got 1/2 mv1 squared plus 1/2 m2v2 squared. So when you combine those two equations, you've got two equations, two unknowns, which are the final velocities. And these are the equations we worked out. We didn't really derive them, but I've written them down. They're pretty handy. So it's a good thing to have handy during your test. Caleb, you also have your hand up?
Hi, Professor.
Can you hear me? A little bit. It just, you're a bit quiet.
Okay, hold on, sorry. Can you hear me better now?
Yes, I can, yeah.
Okay, all right. I just had a question just about like the format of this the solution. So like, yes. I noticed like you have like your V2 prime or V2F prime.
Yes.
Like you inputted your numbers for that in the represent mathematically section.
Yes.
Like is that okay? Because like my understanding, like you would put that in like and evaluate. But like if we were to do this on the midterm, would this be acceptable?
That's a good question. So yes, this would be acceptable if you did this on the midterm. The reason was I actually had two steps, probably better. Yeah, this one didn't fall very nicely. It's like there's two kind of, I first represent it mathematically with these equations, and then I plug in the numbers, and then I have to plug in more numbers to convert it back to the lab frame. So it's a good point. But yeah, this sometimes there's sort of a fuzzy area between the represent mathematically and the solve and evaluate step, because sometimes it's better to plug in numbers a bit earlier.
Okay.
Okay.
All right, thank you.
Sure. Let me, since that's a really good question that Caleb put up, is that let's talk a little bit about this midterm coming up. We can. So midterm assessment 4, which is on Tuesday, November the 17th. So that's actually, I think, 2 weeks from tomorrow. It's after the reading week. Will be done on CrowdMark. So there'll be 2 problems that you have to write out the solutions to using this 4-step method that Caleb was just talking about. So there's 2 points, 2 points, 2 points, 2 points. So 4 steps. Sketch and translate. So, and we haven't done chapter 8 yet, but we will. Chapter 8 is all about torque and rigid body rotation. So, but in both cases, your sketch, so I guess this is more of a chapter 7, isn't it? Chapter 7. Sketch the initial and final states of the process, labeling the known and unknown information. So this would be sort of for both. Label the both an unknown and unknown. You choose the system of interest. That's for both, for sure. Choose the object of reference and the coordinate system. If you're in chapter 8, then you also want to put in an axis of rotation. The simplify and diagrams step, you want to state which simplifications you make to the objects, what are the interactions, what are the processes. If it's chapter 7, you would state which energy types are changing, and you would state whether or not there's external work being done on your system. You'd also, and then this is where you would draw the little work energy bar charts. You've got usually kinetic plus potential plus work, initial equals kinetic final plus potential final. And if it's chapter 8, this is where you draw your force diagram. Except it's not just a point with forces, you've actually got usually an object, like an extended object, and the forces are on different places. So you need to show a rotation axis and where the forces are applied. represent mathematically. This is for chapter 7 problems. That's where you actually write out the equation. All the initial energy plus the work equals the final energy. And then, so each bar in that chart is one of the terms in this equation that you're adding. If it's chapter 8, then you use that force diagram to apply the conditions of equilibrium. Okay. Static equilibrium. And then solve and evaluate is just solve for the unknowns and unknowns, and then ask yourself, does it have the correct units? Is its magnitude reasonable? Are there limiting cases you can look at, that kind of thing? So that's sort of like a rubric idea. Manuela, did you want to ask a question?
Hi.
Hi.
It's about the previous example.
Yes.
I was wondering why it only works when the ball has an initial velocity of 0, because I think that's what you're doing with the 4 minus the 4, right?
Right. So when I derived those equations, I did it assuming that the initial speed of ball 2 was 0.
Why do you have to do that?
Well, you don't, I guess. You could, just the equations are a little more complicated if you've got V2 initial is not 0. You end up with 2 terms. So it's just a little easier to do the math this way.
Okay, thank you.
And then my idea was that if V2 initial is not 0, then you can always just switch to the reference frame that it is 0. Like if I'd written down the real equations with both of them being not 0, they're just much longer and messier looking.
Okay.
Just a little, again, way of saving work. Yeah, you're welcome. And Candy Wang, did you have a question?
Yeah, hi, good morning. For the first question, if we had it on a midterm, our final answer would be 11, right? For significant digits.
Excellent point. Yeah, that's probably true. You'd want to round it to 2 significant figures. That's a really good point.
Yeah, okay. Yeah, that was just my question.
Okay, sounds
Thank
good.
you.
Yep, good point. Okay, I think I'm going to keep going a little bit here. 27. Okay, so let's recap here. This was about this internal energy due to friction. So this delta U internal comes up usually in the final side of the equation, and it's equal to the magnitude of the average friction force exerted by the surface on the object, and D, the distance that the object moves across the surface. You just multiply those 2 numbers. So including friction in the work energy equation as an increase in the system's internal energy produces the same result as calculating the work done by the friction force. So there are sort of 2 ways of looking at this, and we talked about this a little bit last time. This is where it's a bit of a recap, is that if you just take the object as being the system and it slides across a rough surface, then you could say that that surface is doing negative work on the system. And so then you'd put this negative term of negative Fk times d over on the left side. The initial minus this work is equal to the final. My strategy is usually that I think of that as heat being created. So I define the system as including that surface and all that heat. And so that has increased its thermal energy by this amount. So this is part of the final potential energy. So you put a positive number on the right-hand side. But either way, you get the same result. No, either way is correct. Okay, we're starting to get towards the end of chapter 7 now, I believe. So there's a thing called power. So in physics, we have certain words like work, which means something in English, but it also means something very specific in physics. Work in physics means force times distance. It's similar with power. Power has all kinds of meanings in the English language, but in physics, it's something very specific. It's the work done divided by the time interval. So it has units of joules per second. And that's called the watt, named after James Watt, developer of the steam engine. Okay, 1 joule per second equals 1 watt. and a kilowatt is 1,000 watts. Okay. So let's do a poll. Rita raises a 10 kilogram package at a constant speed to a height of 2.5 meters in 2 seconds. It's just it's kind of high, so maybe picks it up off the ground and puts it way up on a top shelf. If she were to raise the same package to the same height in 1 second instead of 2 seconds, how would the work and power change? Watch the poll. Is it A, the work and power would both stay the same, B, the work would stay the same, but the power would double, C, the work would double, but the power would stay the same, or D, the work and power would both double? I think something's going up or staying the same. Okay. 5 seconds to click in. I'll discuss it. And end polling. And 87% of you who voted voted for B. The work would stay the same, but the power would double. So that's exactly right. That's what I like. Oops. The basic idea there being that the power is equal to the work divided by the delta T, right? And what's happened here is that the work in this case is going to be the change in gravitational potential energy. It's going to be m times g times this 2.5 meters. So that's the same for both. Okay, but the power, if delta T goes down, then the power would go up. Okay, so if you divide the delta T by a factor of 2, 1 second, then the power doubles. Let's do another quick poll here. You've got a sports car, it accelerates from 0 to 30 miles an hour in 1.5 seconds. How long does it take to accelerate from 0 to 60 miles an hour instead of 30 miles an hour, assuming the power of the engine is independent of the velocity and neglecting friction and stuff? So let me launch this. Okay, give you another 5 seconds or so to click in. written a couple little hints there. Going once, going twice. Now let's see what you say. Survey says 74% of you are voting for B for 3 seconds. So nobody voted for F actually, even though that was a choice. One person voted for E. Okay, so what I'm thinking here is that in this case, instead of raising something to a shelf and MGH being the work that you did, in this case, you're going from 0 to some final kinetic energy. So the work then done there is just your kinetic energy. And so what's happened here is that the final has doubled. Okay, so V final 2 equals 2 times V final 1 or something like that. It's supposed to be a V, sorry. So what I think then is that the kinetic energy final 2 is equal to 4 times the kinetic energy final 1. So it's gone, you're doing 4 times as much work. And so the delta T is going to be 4 times delta T1. So originally you're 1.5 seconds, 1.5 times 4 is equal to, I think it's going to be 6 seconds. Makes sense? Come on, how are you?
Hello.
Hi.
So I had my hand up for a previous question about the test.
Yeah,
It
no
was
problem.
mentioned that there's lab questions on it, like exactly on the test for lab, because it's only 2 questions, right?
There's only 2 questions, yeah. So yeah, it'll be chapter 7, chapter 8, but presumably in the labs you are learning something about this stuff. So
Okay.
but yeah, it's more relevant when you get a multiple choice test.
Okay. Thank you.
Point. Yeah, sure. And yeah, I am taking people who have had their hand up for a little while, but Josephine?
Hi.
Hi.
Can you go back to the previous thing about the internal force?
The oh yeah, I know what you mean. Yeah, this one.
Yeah, okay. So, sorry, I'm a little bit confused. Does it go on like the left or the right side?
The right. So the way it goes, I should probably write that out. So it's going to be K initial plus UG initial plus the work is equal to K final plus UG final plus this delta U internal. That's how you write it.
Oh, okay. Got
Okay.
it. Thank you. And then one more quick question. For the first example, you put the ball at rest. Is there any other equation where you can not do that, or is that kind of like something you have to do?
Yeah, so it's all about those, back, but those particular equations, which I talked about last class, just for those particular equations, this one and this one, you have that caveat or condition that you can only use these equations if ball 2 is at rest.
Okay, got it.
Okay, sure. And also I'll take Hugo. Again, the hands that are been up so long. Hugo, did you have a question? Okay. What about Sunny? Did you have a question?
Yes, hi Professor. So it's about the poll question that you just did.
Yes.
So I was wondering, it's in work force times distance. I was wondering why it's change in kinetic energy as well.
Yeah, that's a really good question. So yeah, you've noticed work is force times distance, right? But for both of these things, what I did is I said that the work was equal to the energy change. So what I'm saying there is that So really what power is it's the change in energy divided by the time, but that's coming from some work that's being done in the system, right? So in this case, Rita raises a package. The system is the package, not Rita. So system equals package. Okay? It's not including Rita or the Earth. So you've done some positive work on the thing, but in any case, how would the work and power? I guess the assumption there is that work and power are going to be what external work is being done on that little system. So I probably should have defined the system here, and then same for the car. In this case, the engine or the static friction actually is doing positive work on the car, which is getting it up to that kinetic energy. But how do you solve that? If you don't know what the force of static friction is, you just use the kinetic energy.
Okay, thank you.
Because it's what we have our equations for. So, okay, awesome. Okay, so moving along. You may have actually paid for power sometimes if you have Ontario Hydro or Hydro One, I think it's called now. Hydro One. So the company that sells electricity in this province charges per kilowatt hour. So a kilowatt hour is the amount of energy that's used by a power of 1 kilowatt over 1 hour. Okay, and you can actually times it out. It's 1 kilowatt hour is 1,000 joules per second multiplied by 60 minutes per hour and 60 seconds per minute. So this cancels out the minutes, and what you get is just joules. Hour cancels out hour. 3.6 times 10 to the 6 joules. And it turns out that it costs about 13 cents for those 3.6 million joules. So electricity in Ontario, I looked this up for last year, came from 58% of it came from nuclear power plants, actually. 24% of it came from actual hydroelectricity, meaning waterfalls and dams, Niagara Falls primarily. 8% of it came from these big windmills that we have out in the country. 6% of it came from natural gas. Okay, so burning natural gas to heat up boiling water and have steam turn turbines. And then 4% came from solar and bioenergy. So the cost of electricity to be used, the cost of electricity used to be adjusted depending on the time of day you were using it. This is pre-COVID. It was more expensive to use electricity during the daytime hours. But then the government changed the rules so that there would just be one fixed price all during the days, because I guess they're encouraging people to stay at home during COVID. So there's just one cost of electricity, which is now 12.8 cents per kilowatt hour for all hours of the day. And so if you run your dryer for 5,000, which uses 5,000 watts, and you run it for 1 hour, this will cost you, the rate here is 0.128, and the units are dollars per kilowatt hour, right? And so the cost is going to be equal to the rate times the energy. And I guess the other thing you need to know is that the power is the energy divided by the time. And so the energy is equal to the power times the time. Oops. Energy equals power times the amount of time that you're using it, delta T. So it's equal to the rate times power times delta T. So what you pay is going to be 0.128 dollars per kilowatt hour times the power, which is 5 kilowatts, times 1 hour. And so what happens there is that kilowatts cancels kilowatts, hours cancels hour, and you end up with 0.128 $64. So it actually only costs you 64 cents to run that dryer for an hour. Great. I think we're about to ready to move on to the gravity section here pretty soon. Thea, did you have a question? Or Ethan?
Hello. So for this question, why is it weight time energy and not weight time power?
Yeah, you pay for energy. So remember, power is the amount of energy you use per time. So kilowatt, if you just left that dryer on all day at 5 kilowatts, then you'd use you'd use 24 times more energy, right? Or if you only turn it on for half an hour, then you only use 2.5 kilowatt hours. It's a bit confusing. A kilowatt hour is like a joule. It's a unit of energy that you're paying for. A kilowatt means how many kilowatt hours per hour you're using.
Okay. Yeah, I got it. Thank you.
Got it? And Thea, I cut you off?
Hello.
Hi.
I'm sorry, I just left for a second. I noticed that in the midterm 4, we are expected to include different stuff like the bar chart or something like that. Will you do a example question for it so we have something to reference for?
Sure, man. Yeah, all my examples, right?
Okay, great. Thanks.
Absolutely. Good idea. Okay. Okay. So let's move on. I think we're into the last section now of chapter 7 here. So we already did this slide, actually. This is a review of gravity. It was Newton who first recognized that gravity is an attractive long-range force between any two objects. Apparently he saw an apple falling from a tree and he looked beyond the apple and he saw the moon and he thought, wow, I bet the moon is accelerating towards the earth due to the same force as the apple is accelerating towards the earth, towards the center of the earth. It's just that the moon is caught in an orbit, so it's always accelerating and never gets closer. So it's an attractive force. Here's one object attracted, M1 is attracted towards M2, M2 is attracted towards M1, and there's this equation, force is G times M1 times M2 divided by R squared, where R is the distance between the centers of the two objects, and G is this universal constant of gravity, 6.67 times 10 to the minus 11 newtons times meter squared per kilogram squared. So now we have gravitational potential energy in the universe. When two isolated masses, M1 and M2, interact over a large distance, they have a gravitational potential energy of UG equals negative G times M1 times M2 divided by R. And notice that it's not R squared in this, it's actually just R. So when you look at the force equation, there was a squared on the bottom. When you look at the energy equation, there's no squared. And that helps get the units right. We have chosen the 0 point of potential energy at R equals infinity, where the masses will have no tendency or potential to move together. So I think you might remember when we had those rocks that you can always choose an arbitrary 0 point for gravitational potential energy. So what we've done here is we've arbitrarily chosen that when M2 and M1 are infinitely far apart, that's the 0 point. So this is negative. If R goes out to infinity, then this is, well, zero, negative 0. But for any other finite distance, gravitational potential energy is always negative. So I'll just put here. Sort of interesting. So, and again, this is related to the centers of the two objects. So the way this works, gravitational potential energy is 0 when the objects are an infinite distance apart. The only way to add positive energy to a system and then have it become 0 is that if it starts with some negative energy. So the gravitational potential energy is negative when the objects are closer together. So example, if you were to take two objects and do some work on one of them to push it out far away, that would be positive work. And if you get it out to infinitely far away from each other, you end up with 0 total energy. And this is often happens when you've got M2 is the mass of some object, M1 is the mass of the Earth. And if it's near the surface of the Earth, then R approximately equals 6,400 kilograms. Let's do a quick little poll on this. So then you can just use ME times M and RE. So in the diagram below, 2 different configurations of planets, 1 and 2 are shown. In configuration B, the 2 planets are farther apart than configuration A. So which of these, A or B, has more gravitational potential energy? Let's launch the polling. Just give you a quick 30 seconds to click in on this. Okay, there's that equation. So let's see what survey says here. I'm going to end the polling and click in. What do you guys think? Interesting. 66% of you voted for configuration A has more potential energy, and 34% of you voted for B. So it's very simple, right? For RA, here's RB, right? What I think is that RB is greater than RA. So what does that mean? This is on the denominator. So the absolute value of RB will be less, but it's always negative. So less negative is more. RB is smaller. That should say B. You guys follow me there? It was a bit of a hard one. So UGB is less negative. So it is larger. And the way that I think of this is that it takes work to move some objects apart from each other. So what you're doing is you're adding gravitational potential energy to the system. It's sort of like, remember when Rita was taking that box and lifting it up to 2.5 meters high shelf. You're doing work on that object, so you're adding gravitational potential energy. In the same case of these planets, you're pushing them apart from each other, you're adding gravitational potential energy. It's a bit of a tough one. So if you're in the 34% that voted for B, excellent work. So the next question I have is, we now have 2 equations for gravitational potential energy. There's mgy, and there's negative gmem over re. So which is it? How could these 2 equations be talking about the same thing? And I'm here to tell you that they are exactly the same. They just look a little different. And they have a different 0 point. Okay, so we can do an example by thinking of a cat. Remember when I told you the whole point of the 0 point being arbitrary is that it's the change in potential energy that matters more than what it actually is. So it's always the delta U that really affects what's going on. So if you have an example of a 5 kilogram cat, starts at ground level and then walks up to the restaurant on CN Tower, which is 350 meters up. The question is, what is the change in potential energy of this cat? So you can just use 5 times 9.8 times 350, you get 17,000 joules. That's using MGY, our good old equation MGH for gravitational potential energy. So I'm saying that the cat has changed its gravitational potential energy by positive 17,000 joules. So my question is, can we use this crazy equation and get the same result? And I think you can. What you would do is you'd say the base of the CN Tower is at 6,371 meters, if you had the right number of significant digits there. But the point is that, so if that's exactly true, then the restaurant is 6,371 and 350 meters. You follow me? So you've changed your R slightly, and it's slightly more. So then what I did is I subtracted this. I got 1 over one of these minus 1 over the other one. And I plugged that all into my calculator very, very carefully and kept all my significant digits, and I got 17,000 joules. You increased the gravitational potential energy of the cat by 17,000 joules by changing these denominators. And you could try plugging that into your calculator if you want to check me. You gotta be a little careful with not rounding though. Don't round this until the very end. So they're the same. Robin?
I have a question about the last question.
Yeah.
So before that question, we were told that as we when the distance is infinity, we have no potential energy, right?
Yeah. Yes.
So my question is then, is that more than or is that less than any amount that we would have for any real distance?
0 is the highest you can get.
Okay. So our energy is always approaching 0 on the negative side, right?
Yeah.
And then okay.
So gravitational potential energy is always negative, and so 0 is the most it could possibly be.
Okay, thank you.
Okay, really good point there. Okay, so I'm gonna be a little mindful of my time. Let's see what I wanted to do here. What I wanted to do, done the cat thing. So I can mention here that the 0 points of these two equations is very different. The MGY, you're assuming that 0 potential energy is the surface of the Earth. Whereas if you use negative GMM over R, then you put the 0 point out at infinity. So with MGY, obviously gravitational potential energy can be positive or negative. Okay? But since the 0 point is arbitrary, these two equations are physically the same, as long as you're not too far from Earth's surface. This is the actual equation. This is correct, and this one is approximate. And this one's exact. That's the difference. Okay. I don't really know if we have time to do escape velocity. We don't really. I'll just mention that there's something called escape velocity, and then when we come back on Wednesday, I'll talk about it more. So people have considered making a spacecraft launch system using a railgun. If you had some big gun that just shoots something at a certain velocity, then there must be some minimum speed so that you can send something up and it never comes back down. So you know the idea that what goes up must come down. Well, if you shoot something with enough speed, turns out to be 11 kilometers per second, it never comes down. And the way you would work that out is you would say that the final energy must be 0. So the initial energy must be at least 0. So the way we would work that out is we would say that kinetic energy plus UG initial equals kinetic energy final plus UG final. Oops. Final. And you would say that this one equals 0, this one equals 0, this is at infinity. At infinity, it stops. Okay. And then, so what you'd have is kinetic energy initial is very high, plus gravitational energy initial is negative. You use this negative GM ME over R equals 0. So I'll do that a little bit next time. This is what's on the agenda for next time. There we go. I would like you to start reading in on chapter 8, which is extended objects and torque. Torque meaning that you can turn something with a force. And remember, don't forget tomorrow, there's a chapter 7 quiz, which got emailed to you. It's on CrowdMark. I could actually probably put a link to that on the Quarkus, I guess. It's worth 16 homework points, but it's really just for participating and being able to upload something which to me looks like a solution. So I'm going to go to questions, I think. And I think I'm going to also turn off the record so we can all just chat without YouTube soon.